So chapter 10 is about stress transformations and Mohr circle. So just a quick review. So if you have any beam member, any member, so you know that you will have external loads, right? You can have uniformly distributed load, you can have moment, you can have torque, you can have loads. So you can have all those kind of things. In real world scenarios, sometimes you will have multiple different loading conditions on a member. So because of this, you can easily calculate the reaction, right? Using equilibrium equations, you can calculate the reactions. You might also have a normal force. So you can calculate the reactions, and you can also calculate. So for example, you also have torque, so you're going to also have the reaction torque. So because of those external loads, you can calculate all those reactions, right? So once you have the reactions, you can also calculate the internal forces. So how you calculate the internal forces is that you cut a section. So when you cut a section, so let's just say we have cut a section here. So cutting a section is going to expose what's happening inside the member. So by now we already know that there are multiple different forces which are going to be there in the member because of all those external loads and the reaction forces. So different type of forces which we have been talking about individually in different chapters is normal force. We talked about in chapter 4. We also might have an internal torque, which we talked about in chapter 4, I guess. And we will also have shear force. So let's just say this is normal force, this is torque. We will also have shear force. We might also have bending moment, right? And if you have pressure, you might have pressure as well. So there are this, I think we talked about, I don't know, chapter 6, I guess. So we talked about individual internal forces in different chapters. Now we would like to combine all those forces if we have a combined loading scenario. So if you have a normal force, we can calculate stress by force divided by area. If you have a torque, you can calculate stress by TL over GJ. We already know these formulas. We have used these formulas in individual chapters, and we can come up with stresses because of those individual internal loads. If we have shear force, we know, so this torque will actually produce a shear stress. If we have a shear force, we can calculate the stress because of the shear force, which is shear stress, which is VQ over IT. If we have bending moment, it's going to be axial stress, which is MY by I. Also, if you have a hoop stress, then you can calculate PI by T. So we already have calculated these stresses individually in individual chapters. But now, what happens if you have all the forces in a complicated way? So then you have individual stresses which we have calculated, but now we will try to find the cumulative effect of these stresses. We can also see that no matter what the internal load is, there are always going to be two major categories of stresses, right? You either going to have a normal stress or you're going to have shear stresses. Also, uh, we all know that these internal loads vary along the length, right? So the normal force maybe, so you have to cut a section at a given point to expose those internal loads. So the first point is the internal loads are not constant, right? Maybe your shear stress is maximum here, maybe your bending moment is maximum here, maybe your torsion is maximum somewhere else. So different internal loads are maximum at different locations. Also, the stresses, the stresses are calculated along the cross section, so they are also not constant, right? So first thing is the internal loads vary along the length, right? They vary. And if you want to draw a cross section, you can draw a cross section, right? I have drawn a cross section of this member. Let's just say it's a rectangle. So we know this normal stress, this is basically constant along the entire cross section. But what about the shear stresses? We know the shear stresses are not constant along the entire section, right? The shear stresses are maximum at the top and bottom, the maximum at the neutral axis, and zero at the top and bottom. So if you want to draw the distribution of these normal stresses, then the distribution of normal stresses is it's like uniformly distributed in the case of this stress, right? But if you want to talk about the shear stress, the distribution is something like this, right? So the distribution of stresses from the shear force is different. If you want to talk about distribution because of the bending moment, it's also different, right? You have maximum bending moment at the top and bottom depending upon, and the directions are also reversed. So if you combine everything, it's kind of a little bit complicated. You have a variation along the length, and different internal loads are, some are higher at different locations. If you just talk about the cross section, so this is, you also have a variation of stresses along the length. So you can see it's like kind of a little bit complicated to calculate the maximum stresses because different maximum stresses are going to be different, and it's also additive. So for example, this force, if you want to calculate accumulative stress here, you just have to add them together here, but here you have to subtract them uh, on the top. Also, if you want to talk about torque, we know that the stresses are maximum at the corners, and as you go down inside the neutral axis, it goes zero, right? So shear stresses are also maximum at the top, and it's gonna go zero. So that's the shear stresses. So shear stresses are also maximum at the outermost and zero inside. So you can see like the things are not as straightforward, just adding. You have to just figure out and you have to come up with the combined loading. But this is what we will do in chapter 9. But this chapter is about Mohr circle, right? And this chapter is about uh, stress transformations. So this, whatever we have been doing till now, we discussed this in chapter 2, that this is called a macro scale approach, right? This is, this entire thing, we have been talking that we have entire member, we have stresses, we have forces, and that's how we calculate the stresses. This approach is called macro scale approach. And we talked about this in chapter 2. And there's another way which is called micro scale approach, right? So in micro scale approach, what we do is that we just extract a tiny bit of an element from the member, and we call that element a stress element. So for example, if I draw a simple member, and let's just say it is just have a normal force acting on that member. So one way is use macro scale approach, which we have been using in different chapters so far now. And another way is to use a micro scale approach. And micro scale approach is handy when you have combined loadings. So I've explained like you have a little bit of complicated scenario going on. Like it's not straightforward. You have a bunch of different internal loads which vary along the length, and stresses also vary along the cross section. So you have to come up with a combined loading, combined stress. So microscale approach is easier in this way, but let's just, if we want to extract a stress element, what we do is that we're just gonna take a tiny bit of an element and we're gonna zoom in. So what we will get is a cube. So basically our materials are made up of these stress elements. So you have a lot of stress elements, like thousands and thousands of them everywhere. So we have just taken one out and we have zoomed in into this stress element, right? So in its simplest form, a stress element can be represented by two things, which is a normal force, which can be compression or tension, and which will be in x direction and y direction. So this is a normal force. If this is x-axis, this is y-axis, this is going to be stress x, this is going to be stress y. And you will have shear stresses. And shear stresses, these are normal stresses because they are acting perpendicular to the surface area. And you also have shear stresses which are acting parallel to the surface area, which is called tau xy. So if this is in this direction, in order for equilibrium to hold, you also need to have a force in this, a stress in this direction. If you have stress in y direction, for equilibrium to hold, you also need to have a stress in this direction. So this is also stress x, this is also stress y. So you have a shear stress here. So in order to maintain equilibrium, you need an opposite force on the other face as well. And since it's going to create clockwise rotation, right? So you don't see your stress elements like they're usually in an equilibrium position. So you also need a force which are going to acting in the opposite direction to maintain the equilibrium. So this is our stress element which we have extracted out from a member, right? And these stresses, normal stresses and the shear stresses, this we can get from what we have talked here. So we have to select the point. I mean, so for example, if we want to calculate stress at this point, so you can see that because of all different loading conditions, you have generally two categories of stresses. Either you have normal stresses or you have shear stresses. So you can use these stresses and add them together because of different stress components. So you can add the axial stresses together, the normal stresses together, the shear stresses together, and use these stresses and you can write it on a stress element. And this is what we will talk about in chapter 9. So after finishing this chapter, we'll talk about how you can convert all those stresses into a stress element. So that's for the next chapter. But if we have stress elements, then what we're going to do a bunch of things on those stress element in this chapter. So this is called a stress element. This is called stress element. So we could have just used we just could have used these equations and come up with the total stress, and then we can solve a problem. But why we are using the micro scale approach is that it has bunch of different benefits on top of this macro scale approach, because this micro scale approach is really handy when you have combined loading. So I'm going to give you some advantages of why we are studying this micro scale approach. Why don't just use a macro scale approach? Because this micro scale approach has certain advantages over. So why we are using the stress element is because it can easily handle combined loadings, right? So it can easily handle combined loadings. That's why we have like used this stressed element by considering all those combined loadings. This stress element approach, this micro scale approach, is also very useful in stress transformations, because it's not easy to do stress transformation on a normal member, which we have been doing in the previous chapters. So this stress transformation is also a very useful concept because these individual stress elements, they are not always like in this direction. Sometimes they are like rotated as well. So if you rotate the stress element, you're going to change the stresses. So that's also useful. For example, if you have, let's just say if you have a weld here, so in this case this weld is the weakest link. So in this case you would be more interested in calculating the stresses in this direction. So in this case, it would be more useful to determine the stress element in this direction. So if you rotate the stress element, you're gonna change the stresses. So in this case, uh, let's just, so in this case, your stresses are gonna be different. So this is gonna be stress x prime. So when you rotate the stress element, your stresses change. So when you rotate the stress element, sometimes your stresses change. Maybe it will increase your stresses, maybe it will decrease your stresses. So you also have to rotate the stress element and figure out where you're getting the maximum stresses. And that's also it's comparatively easier to do when you're using the stress element than other methods. So that's why we are using this microscale approach. It is also easier, so since we can rotate and we can calculate a bunch of different stresses at different locations, so it's easier to calculate the maximum stresses, right? We can easily calculate maximum stresses, and also it's overall it's overall easier to visualize. So once you have all those combined loadings, you can just put the stresses on the stress element, and then it's easier to visualize this stress element. And also when we'll talk about Mohr circle, then you can just draw also those figures, and you can see where you're getting the maximum stresses, where you're getting the rotation of the maximum stresses. So overall, uh, this microscale approach, this stress element approach gives you whole picture, right? So the stress element will give you a whole picture, so that's why we will be using this. So I'm gonna just draw this member, and I'm gonna draw this. These are the external loads. So if you take one stress element out, uh, so in this particular case, you only have normal force, so your stress element will look like this in this case. So black is for the internal load, this is external load. So if you rotate a stress element, so originally the force was this, right? So these are external loads. If you take out the stress element, these are the internal loads because of these external loads. If you cut a section, you can like get the internal loads as well. These are the same internal loads, but sometimes the stress elements are rotated in different directions. And based on these different directions, you might have different internal loads. So, for example, now you have a new. In this case, this was x-axis, this was y-axis. In this case, now this is x-axis and this is y-axis, right? So you can use stress coordinate systems to convert this force on x-axis and on y-axis, right? So if you just transform this force, you can, some of this force will go on x-axis, some of this force will go on the y-axis. So actually, when you rotate the stress element, you're gonna get some normal force and you're gonna get some shear force. Same will happen here. You're gonna get some normal force, you're gonna get some shear force. So originally, if you rotate the stress element, some of this force will go to this coordinate, and some of this force will go to the shear force. So why I'm telling you guys this is because when you rotate the stress element, and different stress elements are rotated in different angles already, so you're gonna get different stresses. So on top of calculating the maximum stresses which you were calculating in the previous chapter, once you have those maximum stresses, you're gonna calculate the stress element from those maximum stresses. But in addition to that, you also have to rotate the stress element to figure out the maximum of the maximum stresses. And these maximum stresses are called principal stresses or maximum shear stresses, which we will calculate. So, like overall, in the previous chapters, you had internal loads, and from those internal loads, you have calculated stresses, right? If it was a normal force, you calculated normal stresses. If it was a torque, you calculated the shear stress. If it was moment and shear forces, you calculated stresses accordingly. And then if you have all those stresses, you have to combine it. And then you have to combine it and you have to put all those stresses in terms of normal force and shear force on a stress element, right? And why it's useful is that now you can easily rotate because for a stress element, we already have a transformation equation. I'm going to give you those transformation equations. So we're going to use these transformation equations and we're going to figure out the maximum stresses by rotating those stress element, and that those stresses are going to be the maximum stresses, which you will compare it with the material properties. So if those stresses exceed the material properties, then you would consider that this is going to fail, or you can reverse engineer the problem. So you already know the maximum stresses which a material can take given a loading condition. So you can also design a structure as well. So for example, if you want to design a machine, or if you want to design this floor, so all you have to figure out for this floor is how much should be the thickness of the floor, right? So you can calculate the external loads. You know how much snow it's going to have on a yearly basis, what are the wind loading, so you already know how many people on average will walk on the floor. So you know all those things, and you can convert all those as an external load. So once you have all those external loads, you can calculate the reactions at the support, right? This support could be simply supported, could be fixed support, depending upon how they're designed. So you have reactions, you can calculate the internal loads from the floor, right? There would be all sort of internal loads. You can combine those internal loads into a stress element, and then you can rotate the stress element, and that's going to give you the maximum stresses. And if this maximum stresses are exceeding the overall loads you have calculated, then maybe you have to increase the thickness a bit, and then you have to redo the calculation. And that's how usually like engineers design. But this is just the basics, and you have different equations for different materials because different materials behave differently. But that's the whole idea of design, how you design or analyze different structures. So yeah. So now we will talk about how to combine all those stresses and formulate a stress element in next chapter. So let's just draw one stress element, right? So this is a stress element. So we have talked about that based on different internal loads, you'll have all those stresses. Basically, they are of two types: normal stresses, shear stresses. You're going to combine those stresses, and you're going to draw a stress element. And this you will learn in next chapter. But let's just say we have come up with a stress element, right? So this stress element will have two normal forces and normal stresses and shear stresses. So this is a normal stress, stress X, this is a normal stress, stress Y, and then this is a shear stress. So this is normal stress along x-axis, this is normal stress along y-axis, and these four are the shear stresses along the xy plane. So I've written tau xy. So there is a way where you can combine all those stresses which we have learned so far, and we can come up with a stress element. So once we have this stress element, we need to figure out that when we rotate this stress element, of course, these stresses will change, right? Because it depends on the coordinate systems we are looking at. So we need the equations where we can use those equations and we can come up with a new stresses where the system is, or the stress element is rotated. So I'm just gonna, and these equations are called transformation equations. So what we are interested in now is if we rotate that stress element, then of course, let's just say we have rotated this stress element at an angle theta. So if you rotate the stress element at an angle theta, you're gonna change your normal and shear stresses. So maybe it will increase, maybe it will decrease. We don't know yet. We have to use the equations to know. And maybe it will be in tension, maybe it will be in compression. But in this case, I have written, so this is going to be updated stresses because of the rotation. So this is tau xy updated. So till now, uh, we had internal loads, and from those internal loads, we have calculated the stresses, right? We're going to combine all those stresses and we're going to draw the stress element. And this stress element would have basically three components. For a two-dimensional stress element, you will have a stress along x-axis, stress along y-axis, and shear stress along the xy plane. And these stresses are coming from the stresses which we have been calculating before. And we're going to talk about this, but in this chapter, let's just assume we have already determined those stresses. Now we have to calculate the maximum stresses from these stresses, because if you rotate the stress element, you're going to change your stresses, because it's like you have to do the coordinate transformation, and the way it only depends on like your coordinate systems and how you're transforming. So we have to actually calculate those newer stresses, which could be more, which could be less, but we are interested in finding out which particular angle will give us the maximum stresses. And those will be the maximum stresses, which you will compare it with the material properties to figure out if the material is failing or not. So the equations, so in stress element, it's easier to do because we already have an equation for this stress element. And these equations are called transformation equations. So I'm going to just write down the transformation equations for you. So these equations are called transformation equations. So you have transformation equations for the normal stress along x-axis, normal stress along the y-axis, and also you have a transformation equation for the shear stress. So the equations look something like this. So if you want to find a new stress at a rotated stress element, then that's the equation. The equation is stress x plus stress y by 2 plus stress x minus stress y by 2 cos of 2 theta plus tau xy sine of 2 theta. So we will already get those stress x and stress y and tau xy from those combined loadings and combined stresses. And this is those stress x, stress y, and tau xy. And if we want to rotate this stress at a particular angle, let's just say 30 degrees, so this is that 30 degrees. So we can get new transformed stress by this equation. So all we need to know is original stresses from the combined loadings and the angle where we are rotating, and we can get the updated stress x. Similarly, we can find stress y, which is going to be stress x plus stress y by 2 minus stress x minus stress y by 2 cos of 2 theta minus tau xy sine of 2 theta. Similarly, we can calculate the updated transformed stress of shear by using this equation, which is stress x minus stress y by 2 sine of 2 theta plus tau xy cos of 2 theta. So we can use these three equations and we can come up with any stress element rotated along any angle. So in Mohr, in this chapter, stress transformation chapter and Mohr circle chapter, basically the idea is you have to combine all those stresses and put those combined form of stresses into a stress element, because this will help you to calculate the maximum stresses, because different stress elements are, if you rotate them, you're going to change those stresses. So what we are interested in is calculating the maximum stresses. Once you have those maximum stresses, then you can basically figure out that the material or machine or building or any other component which you are designing or analyzing is safe or not safe. So next time, so these are stress transformation equations. Next time, I'm gonna give you some couple of more equations where you can actually use those equations and figure out what particular angle you have to rotate where you will get the maximum stresses. If they are normal stresses, then they are called principal stresses. If they are shear stresses, so we'll figure out the maximum shear stresses as well. So at different angles, you will sometime at a, for example, maybe at a 45-degree angle, you will get the maximum shear stresses. Maybe at some other angle, you will get the maximum normal stresses. So you have to figure out those angles and you have to figure out those maximum stresses. And once you get those maximum stresses, then you can basically compare it with with some yield criteria. So there are different methods where you can compare and figure out if the material will fail or it will not fail.